For decades, dietary fat has been the ultimate villain of the grocery aisle. We've stripped it out of cookies, banished it from yogurt, and blamed it for pretty much everything. You may or may not know this, but your brain is actually 60% fat. So eliminating fat from your diet would mean that your brain could literally stop functioning. So why does fat have such a bad reputation? Today, we'll talk all about fat, including how it's digested, how it's stored, and the differences between the types of fat, meaning how to spot which ones should be avoided and why they should be avoided. I read a ton of research papers, so I'm going to attempt to break them down in a digestible way. Get it? Digestible. Anyways, let's get into it. I think it's important to start with why we need fat. You can think of fat as your body's ultimate multi-use tool. Fat serves many purposes within the body. First up is energy storage. While carbs give you quick, fast-burning energy, fat is your long-term battery backup. 1 gram of fat gives you more than double the energy that a gram of carbs or protein does. Secondly, fat is necessary in order to get proper vitamin absorption. I feel like this isn't a super well-known fact, but many vitamins such as A, D, E, and K are fat-soluble vitamins, meaning they can't dissolve in water. They need fat to act as sort of a delivery vehicle. So without fat, these vitamins would just slide right through your digestive tract without being absorbed. Lastly, fat is an important structure for protection. Fat basically cushions your organs like bubble wrap and allows your brain to communicate with your body. In simplified terms, the wires that hook your brain to your body have a protective coating called the myelin sheath, which is made of fat. Without this protective layer of fat, the wires could leak electrical signals, moving more slowly and losing information on their way down to the body. In fact, human breast milk is almost 50% saturated fat because of how important it is for babies to develop this myelin sheath while their brains grow and create connections. Now we'll go into the structure of fat. This is just to give a better idea of how fats differ, because it all has to do with their structures, so just bear with me for a couple of seconds as I give a boring structure talk, because structural differences are what make fats good or bad. Under a microscope, most of the fat we eat is structured like a triglyceride, meaning it's shaped like a tiny fork made of carbon and hydrogen atoms. These 3 carbon and hydrogen fork prongs are the fatty acids. So the main body of the fork that holds those prongs together is made of glycerol. So together, the whole fork, meaning 3 fatty acids held together by glycerol, make up a triglyceride, and a triglyceride is fat. The determining factor for a good or bad fat is the shape of those 3 fork prongs, the fatty acids. So now let's categorize types of fats based on their structures. First up, we have saturated fats. Saturated fats contain long carbon chains, each with hydrogen atoms attached to them. Because these prongs are straight, these molecules are packed tightly together, which allows them to remain solid at room temperatures. So think of butter, coconut oil, or the fat on a steak. For a long time, scientists thought that saturated fats directly clogged arteries like sludge in a pipe, but modern research shows that it's nuanced. While eating too much saturated fat can raise your LDL cholesterol, which is the bad version of cholesterol, it doesn't mean it's pure poison. Many current health guidelines just recommend moderation, not total removal from a diet. These guidelines suggest keeping saturated fats to less than 10% of your daily calorie intake. Next, we have unsaturated fats. These are the good guys of the fat world. Somewhere in the carbon chain, or those fork prongs, there's a double bond between the carbons that creates a physical bend in the prong. Since it's bent, it can't stay as sturdy, meaning the molecules are not able to pack as tightly together as when the prong is straight. So because of this, they melt at lower temperatures and are typically liquid at room temperatures. These are your plant oils, avocados, nuts, and seeds. Within unsaturated fats, there are 2 groups. There's monounsaturated fats and polyunsaturated fats. This just means the number of bends in that fork prong. Monounsaturated fats only have 1 bend, and polyunsaturated fats have multiple bends. Polyunsaturated fats are super healthy for us, but we don't produce them naturally, so we must obtain them through our diet. This includes the famous omega-3s and omega-6s found in fishes like salmon. Lastly, we have the real villain of the fat world, trans fat. Trans fat does occur naturally, but in extremely small amounts in products like dairy. The dangerous trans fats are all industrial. Back in the 20th century, food manufacturers wanted a cheap way to turn liquid vegetable oils into solid fats to make packaged food last longer. So, they blasted liquid oil with hydrogen gas, forcing those bent chains to straighten out. Those now straightened prongs create a trans fat. Since trans fats do not typically occur in these concentrations, our bodies are really bad at digesting them because they're unfamiliar with this fork shape that's been manually changed. These fats raise your bad cholesterol, lower your good cholesterol, and trigger inflammation. They're so universally bad that many countries have banned artificial trans fats entirely. I'm personally from Canada, so for me, trans fats are now illegal in our food supply. That's just how bad they are. So, what actually happens when we eat fat? Fat faces a unique challenge because it's hydrophobic, meaning it hates water and refuses to dissolve in it. So it sticks together and clumps to get away from the water. Since our digestive tracts are water based environments, processing fats is like trying to wash a greasy pan without dish soap. When fat arrives in your small intestine, your gallbladder releases bile, which is a substance made by the liver. Bile acts like dish soap. It surrounds the fat and emulsifies it, meaning it shatters the large clumps of fat into small droplets. As long as the fat is not stuck in a big clump, it's able to be digested by our regular enzymes. So, with the help of bile, fat is broken down. Next, enzymes from your pancreas called lipases arrive. They chop down these broken down fat molecules into individual fatty acids, meaning those individual prongs of the fork. These prongs are then absorbed through your intestinal wall and sent one of two ways. The fat is either sent into your bloodstream to deliver energy to your cells or sent into storage for later use. While our body uses the same tools to digest all fats, the speed and difficulty of this process depends on the type of fat eaten. Remember how unsaturated fats are fluid and bent? Because they're already liquid droplets, our body's enzymes can surround and chop them up with ease. But saturated fats enter your system as a more dense structure. And research has shown that your body takes twice the time to digest these fats in comparison to unsaturated fats. Chemically, trans fats are unsaturated, but because they've been artificially straightened out, they act like saturated fats. Now, the liver enzymes made to digest naturally shaped fats are unable to digest these fats because of their weird structure. And these trans fats just sit around and clog internal cellular pathways. And this confusion causes your liver to pump out more bad cholesterol and store an abnormal amount of fat inside the liver rather than normal body fat stores. When your body decides to store these fatty acids, they're clustered together into a structure known as adipose tissue, most commonly known as body fat. There's actually three different types of adipose tissue: white, brown, and beige. White fat is designed for long-term energy storage and insulation, but brown fat is a metabolic powerhouse. It's packed with iron-rich mitochondria and expresses a protein called UCP1. When you're cold, UCP1 causes your mitochondria to burn calories to produce heat. Finally, beige fat represents a transitional state. When you exercise or expose your body to cold, signaling molecules can prompt white fat to undergo browning, turning into highly active beige fat that burns calories to keep you warm. This process is why many people say that repeated exposure to extreme cold, such as cold plunges, triggers the body to recruit more calorie-burning fat cells. Well, that might sound easy. The energy burned during a cold plunge isn't really significant. The real benefit of browning fat is the improved long-term overall metabolic health. We've already talked about the necessity of dietary fats, but why then has fat become an issue in most modern diets? Well, it's no longer the old ages where we had to hunt for our food and store fat in case we didn't get a meal for the next couple of days. Calorie-packed foods are now available 24/7 at the push of an order button. They're extra accessible, extra cheap, and are designed to trigger those ancient survival instincts that tell us to bulk up so that we have food storage in case of starvation. We know that adipose tissue is natural and essential, but when we constantly supply it with more energy than it can burn, we run out of safe storage space. Our bodies have no more space under the skin as subcutaneous fat, and start packing it deeply into the abdomen as visceral fat. Visceral fat wraps tightly around your vital organs like your liver, your heart, and your intestines. Visceral fat is highly metabolic, but not in a good way. When visceral fat gets overstuffed, it gets physically crowded and stressed out. Because it sits so deep in your abdomen, it drains its contents directly into something called the portal vein. This is a major biological highway that goes straight to your liver. Its typical purpose is to carry blood from your intestinal tract, spleen, pancreas, and gallbladder directly to the liver for filtering and detoxification. So, visceral fat entering this vein means it's just dumping fats into the liver, causing fatty liver disease. Visceral fat also suffocates your cells of oxygen, since it expands around your abdomen and leaves little space for your organs and cells. These cells panic and send out distress signals in the form of inflammatory chemicals. Due to the portal vein, these inflammatory chemicals hit your liver. So now your liver just becomes overwhelmed by the excess of fat and inflammatory signals, and it begins to ignore insulin, the hormone meant to clear sugar from your blood. This is called insulin resistance, and it's the direct stepping stone to type 2 diabetes. At the same time, this constant state of inflammation spills over into your bloodstream, damaging the lining of your blood vessels, causing plaque to build up much faster, creating massive cardiovascular strain, and skyrocketing the risk of heart disease. So, the problem isn't that body fat is inherently evil, it's that our ancient survival system wasn't built for a world of infinite, effortless calories. And this is why a high body fat percentage leads to so many health issues. To end off, I'm going to rapid fire answer some questions that either I wondered while reading all these research papers or I saw commonly online during my information search. But I just want to preface that my answers to these questions are based on my personal comparison of published research articles. There's always research that can point in differing directions, but I have tried to give answers based on the research with the most scientific backing and experimental findings. I don't even think I can count the number of seed oil articles I saw while researching. So, probably one of the most commonly asked questions, are seed oils bad? This is a massive internet debate right now. The claim is that because seed oils are high in an omega 6 fat called linoleic acid, they convert into inflammation causing compounds. But in clinical trials, less than 1% of that linoleic acid is ever actually converted into inflammatory markers. Now, you might say, but seed oils are all over highly processed foods, they must be bad. Well, it's the processed food that's bad for you, not really the liquid oil itself. Question 2 that I saw online was, does intermittent fasting allow you to burn fat faster? You've probably heard that if you restrict your eating window, your body switches into a magical fat burning state. Well, there is a bit of conflicting research here, but large clinical trials that compare fasting to standard daily calorie tracking reveal very little difference. This result, though, seems to depend on whether the population used was obese or of average body weight, where fasting did provide additional benefits to obese populations, but not really added benefits for those of average weight. When your body goes without food, it will tap into your fat stores for fuel. But over a 24-hour cycle, your total fat loss is determined by your overall energy balance. However, if fasting helps you naturally eat less without tracking, then by all means do it. But it's really just another tool to manage energy intake. A question that I wondered myself is where body fat goes when it's broken down and it's lost. Through our metabolism, fat molecules are actually broken down into carbon dioxide and water. This means that you actually exhale about 84% of the fat you lose through your lungs, and the rest leaves as water. And let's end off with a fun fact. Cold water fish are super packed with those unsaturated omega 3s, specifically because those liquid fats stay fluid in freezing temperatures due to all the bends in their fatty acid chains, which is how fish prevent themselves from turning into a solid block of ice in freezing waters. So, from insulating your thoughts to quite literally letting you breathe it away, fat is easily one of the most misunderstood pieces of human biology. Thank you for watching. I really appreciate your support, and I hope you continue to learn with me.